Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 21 of the Lemma Journal Club.
Why is the Lemma Journal Club?
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about the research paper Active Solids, Topological Defect Self-Propulsion without flow. Linnea has messed up her audio setup, so we're going to have to pause right off the bat.
My microphone is also drooping. Maybe the temperature or something changed in our house.
Linnea, this is a earnest question. We know all these people, but why did you pick this paper?
Yeah, I picked this paper because I want to start thinking about things other than phase separation. And one of the ideas that I propose in my in my faculty research statement is to apply active theories to other material states. So not just liquid-liquid phase separation, but kind of viscoelastic bodies or membranes, and do this kind of active foams that you did in your PhD. And this seemed adjacent to that idea, the idea of active materials that are not liquids. And you're giving me such a skeptical look.
I'm skeptical about several orthogonal things right off the bat.
And so we had pulled up this paper from our weekly update, and I am also trying to not spend a million years picking papers.
Yeah.
So I went mostly off of the title and the brief summary, and I was like, it's short, we'll read it. We'll see. I'll leave it there for now.
It's a little bit longer than I was expecting for a PRL paper.
For a PRL, yeah, it was I felt like almost a page longer than they usually allow you to do.
Some skeptical things that I'll just list off right off the bat. One is that while you were describing why you picked this paper, you gazed wistfully off into the distance as if you were thinking deeply about science, which is very poetic and apropos, but you were completely not facing the microphone anymore. And so we'll fix that in post. The second thing is, active pneumatic fluids are a viscoelastic material. And I feel like the theory captures that just fine. This is a purely solid material covered in this paper.
Yeah.
I can imagine things that I would study that I might maybe model purely as a solid, but I cannot imagine, none of the things that you said just now, such as foams or membranes, could I imagine a purely solid description being a good description.
Okay. Yeah, I hadn't thought that when I picked the paper, right? I was like, a purinoid could be mostly solid.
Oh, yeah?
Sure. I mean, it could be like a hydrogel, right?
A hydrogel is a mostly solid thing. Yeah, I guess so.
And so, I was wondering if this
what an interesting
kind of thing,
idea. Because when you see, say, membrane, I'm thinking mitochondria, a lot of people, okay, fine. It's interesting. So you're going to look for pneumatic defects, not at the scale. Here they're talking about, their reason why they want to do this is because they're thinking about
Hydra.
My God. Whoever is the Hydra fan on this paper, and I have a bad feeling that it's Fridtjof, shut up. No, it's just you can be a Hydra fan. You could have used that once. It doesn't need to be every fifth sentence. Jesus.
I was also bothered by the Hydra. I thought it was
so bothersome.
It was pretty bothersome. And it was always one example of which is Hydra. And it's either make this a paper about Hydra or list some other examples.
Yeah, it really, it's not important. It's just, anyways.
It's not important for the science.
Someone on the paper loved that Hydra finding that happened a year or two ago. But the point is, in my science, there's all sorts of cellular arrangements that look like they're pneumatic liquid crystal things, and maybe it would be useful to describe stuff via pneumatic liquid crystals. Physicists and biophysicists really want this to be true because it would take one of the theories that's more beautiful to us and make it something that we could actually apply to systems. I think if it does turn out to be true, we're really jamming it in there, right? Hydra. It's an example of one place where it works. But I like this paper. I did like to think of I should specifically be keeping an eye out for defects that are moving backwards or are moving against my intuition, which is some of the things that they say can happen in these active solids. It's interesting to hear you thinking of your much more molecular systems being solid. Because when I was reading this paper, I was thinking Hydra and bigger.
Yeah.
Right. And I was thinking, I want to describe a collection of cells as a purely solid thing ever. In what situations do I think cells are really not sliding past each other? And I was like, oh, there's a lot of situations. Maybe I should look over my data to see this. Oh, I see a hawk in a tree right over there, just kind of scoping.
All the chickens are inside the barn.
He's not up high in the tree. He's right at our level. Interesting. He's just chilling there. Yeah, so it's interesting to hear it down at the molecular level. Oh, yeah, okay, fine. The paranoid could be a solid.
It could be a solid. It's unlikely that it's a nematic in this way, right? Like none of the components are ordered or like have this anisotropy in like rod-like shape. But it's still, it was an intellectual concept I wanted to explore, especially from a theory paper where I often get a lot of inspiration.
The video for this episode is just going to be these 3 meh.
I was thinking we should email Ray. Isn't he doing Hydra for his postdoc? Maybe he has a shitty video we can, or a unanalyzable video that he can give us.
Ray, you mean Ray Adkins, not Satvik Ray?
Yeah.
I know he's doing some sort of jellyfish-like creature, but you think he's doing Hydra?
Yeah. A fun video.
For a second, I thought you were telling me that Satvik Ray was working on Hydra in Chicago.
And then one other thing before we delve into the actual content of this paper is that
No, I didn't get to finish my thought.
Oh, okay.
Which is that it's going to be these 3 shitty movies. Hopefully we actually get a movie from Ray Adkins, which would be beautiful. But what I want this movie to be is just a movie of this falcon that's just chilling. I guess it's a Cooper hawk, right? But it's just chilling, 20 feet away from us while we're describing this. That's what I want the video for this to be. I might see if I can grab. Okay, what are we going to talk about for this paper? I feel like we more or less covered it. No, we haven't gotten into
Okay, I wanted to say a few things before we get into the actual paper. The first is that it's co-first authors for Fridtjof and this guy, Myles O'Leary.
Yeah, good for pointing that out. I didn't notice that.
And Myles O'Leary is at Princeton.
Oh.
So have we met him?
Yeah, I'm sorry. Do you know who this person is?
I thought. I mean, they must have met at a KITP conference, right?
He works for Ned Wingreen. He's in the same group as you.
Really? Ned's group meetings are 5 p.m. on Wednesdays. So I have not been since Asya was born. And then the other thing in the preamble is received 21st of February 2025, published 6th of February 2026. So it's a PRL paper. It took a year.
What the hell could they have possibly been bickering about in review for a year for this paper?
I mean, I assume it just was very slow with people like Fridtjof was on the job market and moving to Germany and...
Yeah, but that's there's no experiments in this paper. They just did some math, right? Math is math. It's not like it's going to be wrong, especially not with this crew. What in God's name did they think they were doing putting this in? God, it's out of control. It's completely out of control. There's nothing to review for this paper.
Yeah. Well, yeah, I was just sometimes people will say, oh, just put out a small paper or about blah, blah, blah. And it's just another reminder of no paper is without its headaches.
I was a little bit...
Because this paper seems like it should have no headaches, right? Like they were just communicating an idea that they had at a conference. And that's another, it could have just taken that long to get reviews. Again, we talked about on a previous episode how PRL is becoming not friendly towards biophysics.
The review process, right? It went to Ray Adkins, and Ray Adkins was like, "Please add more Hydra." What? It's math, right? Okay, so the paper, real quick.
In this letter, we propose a minimal model for defect self-propulsion in a nematic active solid. A linear elastic medium with an embedded nematic texture that generates active stress and associated elastic strains. Thought that was a good summary.
Yeah.
Right in the abstract.
It's active nematic liquid crystal, except for now it's not liquid. Depending on how you set up the elasticity, you can get +half defects to move backwards That's the thing that I thought was cool.
Yeah, the self-propelled, and my intuition is still not great, but I thought one of the interesting findings was that they do see self-propulsion of the defects. So it's not just defects relaxing back to the lowest state. It's actually they're moving in this steady state.
Wouldn't have guessed.
Yeah, me neither.
As far as you picking theory papers, this is a good theory paper to have picked.
Yeah, I think it's the first theory paper that you could argue one of the chicken attractors papers was purely theory, but I think this is the first really pure theory paper where there's no...
Two things happened really quickly at the beginning of this paper. The last author on this paper is Cristina Marchetti. The Lemma Journal Club started in 2015. You and Pooja formed it, and you invited me to it. It started with the two of you trying to wrap your head around a Cristina Marchetti review paper. And we read that paper back and forth over and over again for about a year. And the difficulty with reading that paper was getting hit by these things like this, frank elastic coupling.
Like you look at it and you're like, well, maybe I should just skip this because there's so many terms and I don't know what any of them mean.
And so what I was thinking, two things. One, we spent a year on that paper learning how to read that notation. Another thing that happened about a year ago is during Passover last year, spent all of Passover. Passover is a terrible holiday where you spend a tremendous amount of time doing nothing. I spent all of Passover writing a pneumatic liquid crystal simulator that you could put on top of a Pong game where the pneumatic liquid crystal advects the Pong ball.
Yeah, I remember.
And that actually made me because I was tuning the elastic parameters and the shear modulus and the bulk modulus, and I was tuning everything
and seeing what happens
to make it feel good as a game, I became an order of magnitude more comfortable with these equations. That not only did I spend a year learning how to read the equations, but then I spent a couple of days really tuning one equation at a time and seeing how it made the pneumatic liquid crystal feel. And so two things really quickly happened to me in this paper. One, I was like, man, this is 1,000 times easier to read than the first active matter papers I read, because I look at the equation and I'm like, okay, I know how this works, and I move on to the next equation. And then equation 3 is the last equation I bothered to read. And that's bad, right? Yeah. I kind of tried to tune back in around equation 9, where I was like, I'm missing.
Equation 3 is where they start to say C extended note, blah, blah, blah.
Yeah. So I had some trouble tuning in to the math.
It does really make me miss, in my PhD and a little bit at the beginning of my postdoc, I would look at something that I was seeing in my experiments and I would write down the shittiest PDE that I thought could describe the dynamics. And I don't do that anymore. And it's because I'm not reading these papers, but to just be able to write down something really like anything that's mathematical, I think is something I need to come back to.
Should we talk about some things that they find in the paper? One of the things they say fairly early on to justify their model. I'm always surprised the way that people try to justify a purely elastic or a purely viscous model. Each time I'm pretty freaked out by it. But here they justify that they consider adiabatic dynamics in a regime of quasi-static force balance where the pneumatic texture remodels on a timescale much slower than that of force equilibration through deformations. And they justify this by saying, without citations, this assumption is justified in a tissue where force balances on short timescales, seconds to minutes, compared to the remodeling of the actomyosin fibers that form the pneumatic texture, hours.
Yeah, I highlighted this in red. It felt like...
Is this known in any system?
They made this, this assumption is justified. That's such a strong statement. I would have said at least is likely justified.
I would just...
or we are making this assumption.
Yeah, we are making this assumption.
Because it could be possible that
it's deeply unclear to me that this is true.
Yeah.
I wouldn't bet any money on it either way, but where's a citation if you're going to make that sentence? What did they do while they were in review for a year? Jesus. The next thing that I had some trouble with, as we say, equation 3, is concerned with the rotational viscosity. I guess you only care about the rotational viscosity because there's no advection that you can't move around. So all there is rotation.
Right. I mean, even bouncing earlier, this chi-b coefficient, this is not in active pneumatic fluids, right?
Yeah, this strain ordering coefficient.
Yeah, strain ordering for chi b greater than 0, pneumatic order decreases or melts in regions of compressive strain. And then they talk about that this is a new term.
Yeah.
One thing that was unclear to me is like, if you don't have this coupling, do you get self-propelled defects? Okay, so some things that you can, so that there's activity, which is dictating the strain.
Yeah.
And then there's coupling between the activity and the elastomer, the pneumatic elastomer. And that's mediated by this chi parameter. So there's activity in the stress terms. There's this alpha tilde and alpha tilde B, which they say are effective active stress.
Yeah, I see. And then there is an activity directly in the order parameter Q as well.
There is an Q? Oh, which is equation 4?
Term of 2. Or sorry, the last term of equation 2.
Of equation. That's the active stress. I mean, that's the stress. That's what I was talking about. The stress has these two activities, and the free energy only, like, it has strain, right? But it doesn't have stress. But stress and strain are related by this stress equation.
The thing on the left-hand side is stress.
Yeah.
Inside the stress is Q, which is the pneumatic order parameter.
But Q does not depend on activity.
Well, it's multiplied by alpha tilde.
Yeah.
Which is activity. So the relationship between stress and the pneumatic order parameter is dependent on the activity term.
I
right?
agree.
Yeah.
There are other things linking okay. Yeah, you're right. That the activity is also somehow linking. Although this activity, also depends on a chi, which is not chi b, some other chi.
Is it not? I think it is the same chi.
There's alpha b equals alpha b minus chi b.
Yeah.
And alpha regular is alpha minus chi.
Chi b is specifically the strain ordering chi.
Yeah.
And then I think
the other chi is not a strain ordering chi.
The other chi is...
The coefficient chi accounts for strain alignment of pneumatic order along the direction of deviatoric stress U, aligning them when chi is greater than 0 and anti-aligning them when chi is less than 0.
Right. And then the coefficient chi b describes the coupling of the pneumatic order to the isotropic train. We have uniform equilibrium when chi equals chi b equals 0. Mm-hmm. So they're very similar objects.
Okay. Yeah, I agree that they're similar.
I was thinking the whole time that I was reading this, who I would really... This is why I got confused when you were talking about Ray at the beginning. I was like, who I would really like to be reading this with, who used to come to Journal Club? Satvik is the kind of person who would look at this and say something interesting about it.
Yeah, that's true.
Whereas we're just like poking it,
anyways,
seeing what we get out.
This coupling, this strain ordering, I thought was confusing to me as to how important it was to see the dynamics. You're saying it's essential to see any of the activity.
I don't know. Okay, so let's think about this for a little bit. This chi b lives both inside the activity term, and it also lives inside this free energy term. Yeah, but the thing with these theories is that there's always it's always hiding pretty much everywhere. Like activity is hiding pretty much everywhere. And in this case, this strain ordering is also hiding pretty much everywhere. So to say if I drop it just from, let's say, equation 1, but allow it to sneak in through the activity anyways.
Yeah.
Yeah, I mean, presumably that breaks some symmetry that makes it no longer valid mathematics. But let's say we find a way to do it. I think it does still sneak in.
Okay, so that it's part of the system, essentially.
Yeah.
That in order to put activity into an elastic solid, you have to have some parameter that you tune to couple the activity to the
at least the
pneumatic
way
ordering
that they've done it.
Yeah.
Sure.
Okay.
So then, we get to figure 1 shortly after this. And the figures do not have, I don't know if this is maybe PRL's format, but the figures do not have sentences. So we can't even say, the sentence, it's not a sentence. Or
that there's no figure titles.
There's no figure titles at all.
Yeah, I don't know. I can't remember if that's something that's PRL specific.
So illustration of the elasto-pneumatic coupling is considered in our model. So there's a coupling from pneumatic order to elastic strain, which comes from alpha twiddle and alpha twiddle beta. And then there's a coupling, not beta, alpha twiddle B. And then there's a coupling from elastic strain to pneumatic order, which comes from chi-b, which is the strain ordering, and chi, which is the strain alignment.
Okay.
So if we could if this figure was a little bit better, I think a lot of our confusion about this would
go away. Yeah, there's so many arrows.
Do you think Mark Bowick or Cristina will ever talk to us again after this episode?
I don't imagine that they will ever listen to this episode.
Mark Bowick, if you're listening, you lent us a book about 7 years ago.
A Debt to Pleasure.
A Debt to Pleasure. It's a terrific book, and we've just stolen it.
Okay, so the origin of the interesting finding. So like the first section, the first result, I would say, from the theory is this self-propelled plus half defects. And the origin of this is that there's some gradient in strain across the defect core that allows it to propel itself.
Yeah, and this propelling itself is something that I wouldn't have guessed.
And one thing that's true in active fluids, right, is that these defects, the direction of movement depends on the extensile or contractile stresses.
Yeah.
So it wasn't clear to me what stresses they were imposing here. I think they were doing contractile.
I think because it's Hydra, so they're going to say everything is contractile.
And this 1A, the deviatoric, looks contractile to me. And so
that's true.
I think it's moving, like if you were to flip the sign of this alpha tilde.
Yeah.
That it would move in the other direction.
Extensile but I think you're right. And they do say, in particular, this allows a system with contractile activity to have a defect move towards its head, move the way we normally think of, when this chi-b is negative, i.e. when extensile strain reduces pneumatic order. So that, essentially you have it's not getting infected by fluid velocity anymore. So you have a secondary thing, and it allows you to flip the sign one more time, which is kind of like experimentally, it's very nice. It's also like you're getting close to the point where you can explain anything any way you want. So it's starting to become a little bit less helpful.
And then they talk about this defect pair unbinding, which I found really not
They only talk
useful.
about it for a paragraph, so I don't
Well, they give it a whole figure.
The defect pair unbinding? Because I didn't find it interesting either. Okay, sure, let's go.
The thing I found odd here was that in an active fluid, to get a plus half and a minus half defect, these are like nucleated continuously through the activity by the bend instability. So what is producing defects in this system, and why would their initial separation, what sets the initial separation distance? I would assume initial separation, if this is an active, like a similar mechanism to the active fluid, I would expect initial separation to be 0 all the time. And in that case, according to their plot, you would never see unbinding.
I kind of think, that's a good question.
So is there a dynamical steady state here, or it's just that the defects, can you create and annihilate defects in this system?
You have activity, which is changing your order parameter over time. It's not clear to me that generates a defect, but I'm just spitballing. I'm essentially saying it would be very easy to say, look, it's generated by geometry, by your boundary conditions.
Yeah.
But when we're talking about
this is what happens
right?
is what happens in the confined case, which I think was much easier, more tractable.
When we're talking about pair unbinding, so let's say we really have just an infinite space in which we have no defects, and you can see that the activity is generating stress. It's even unclear to me what happens actually in their simulations. If you just have an infinite space with no boundary conditions,
would you get defect creation? Yeah.
Periodic boundary conditions. Would you get defect creation? I'm sure it's supposed to be clear to me from reading this, but...
Yeah, it was not clear to me, so...
Because, there's no, is there any elastic turbulence thing here?
Or is this just if you... Most interesting in the confined case, or if you start in a bulk situation where there's a lot of defects already present, and then turn on activity.
Yeah, the movies are... very finite liquid crystals in which they've already created their defects, and they have pretty tight boundary conditions as well. So they don't have anything like my plasma Pong simulations where there's a giant wide field.
Oh yeah, your plasma Pong simulation should answer this question for us.
If I can get
the elastic stuff in.
Solid.
Yeah.
It is I was able to do my elastic Pong thing because I was able to crib from many different theories of active nematic liquid crystals. And I was able to email the authors and say, how did you do this? How did you do that? Anyways, we'll see what I get.
Okay. Yeah, it might not work. But it would answer an interesting, or what I think is an interesting question. Okay, and then we move on to the interaction of plus half defects in a confined domain.
Which is like the interesting biology thing, yeah.
The interesting biology thing, and this like callback to the Acini Mike Norton paper for active liquid nematics. And you get these rotating defects or the stabilization of these spirals, a spiral plus one defects, which I thought was neat to see, would be cool to like compare this to some experimental system.
Yeah, it is. Again, I'm going to say dangerous on the second time, right? Like if you get these plus one defects, if you get this situation 3 or 4 in figure 3 on an experimental basis, like one can both say nothing experimentally looks that way and everything experimentally looks that way. That we again have like, because we have a lot more freedom in this theory to make different things happen, it is either very easy to pin everything to this theory or very hard to pin anything specifically to this theory, which makes me a little bit worried that I highlighted this bit about forming plus one defects in red because this figure 3, man, you can make anything in biology look like that. So it's a little bit concerning.
Yeah. I did briefly click on one of these papers. I'm not going to open it now again because I'm worried about my computer, but reference 5, integer topological defects, organized stresses driving tissue morphogenesis. And I didn't get to look at what organism it was or if it was an organism in an organoid.
No, it's just patterned cells in like little microwells.
Okay. Yeah, I mean, this seems like in vitro-ish system where you could try to move around this phase diagram.
It's a beautiful paper.
It's from the first author, P. Guillemot, wrote a lot of active nematic papers when we were PhD students. So I think this is his postdoc work.
It's beautiful.
Might have been a better paper to choose for Journal Club, but I didn't know it existed. So
yeah, there's a couple citations that I read through. A lot of Hydra papers.
A lot of Hydra. Yeah. I think the thing that would be convincing that this theory was applicable to anything would be like being able to move through this phase diagram by changing like the twist angle or...
Well, I think it's certainly applicable to things. It's just a question of like, I think the active matter community is struggling where the soft matter community was struggling 10 years ago, which is like there's a difference between something being true and being useful.
Yeah.
And that's where we are now. I have no doubt that like math is math. It's true. I have no doubt that there are some systems that are going to be describable via this math, and that will be beautiful as we find it. But the lifespan of this paper depends on its usefulness.
Yep.
And that's actually why the Hydra really bothered me, is because I'm like, if this paper is still being read 30 years from now, because it did turn out to be useful, this Hydra stuff is not going to age well. Like it already doesn't age well, and Hydra is in vogue right now, right?
Yeah.
If you have to read this as an undergraduate 30 years from now in a biophysics class, and you're like, why are they so obsessed with Hydra? They try at the end to really like move it towards applications, right? So they have the role of the substrate traction.
Yeah.
And they talk about tissue studied in vitro are often attached to a rigid substrate, which, at least this time they provide citations for. Although one of their citations is 5, where I would argue that ain't a tissue, but, maybe you can call a collection of cells a tissue.
Well, they say studied in vitro.
Tissue studied in vitro. When I hear tissue studied in vitro, I think what I do, where you've taken like a small bit of an organ or something.
I feel like the in vitro term means something different to everybody.
That's true. When I feel like the word tissue overrides that here. A tissue is like a natural collection of cells.
Okay.
And you could have a tissuoid, like you have an organoid, you could have a tissuoid. I guess all organoids are tissuoids, but maybe my nomenclature is not correct. They talk about trying to apply it in that situation. It just gives them more degrees of freedom, which I, again, don't love. And then they talk about, I think probably my most disliked part of the paper is considering this model on top of morphogen concentration gradients.
Yeah.
Which I really didn't appreciate.
I just think that this is like... This I was not surprised to read, right? Well, A, for somebody from Princeton, and B, from Fridtjof, who is thinking about these things a lot in
I just think that when you think about these
systems.
things, you have to think about... I guess it's just a sentence or two
It feels very like a theorist, like, yeah, oh, there are these other fields that we could think about, and wouldn't that be cool to see what those do?
Yeah, it's okay. It's okay.
Yeah, so I feel that this paper, I think it's a good paper. It's a good little PRL thing. I think it was a dud as a pick for Journal Club.
Yeah, but I'm happy we read it.
I'm happy we read it. I don't know if we needed to do an episode on it, right?
We'll
and
see.
I kind of read that, or I kind of realized that about halfway through reading it.
Yeah.
Right? And
I
it was like,
realized it. I was like, oh shit, I really don't want to talk about this paper out loud.
where we're just like, we're not the, I mean, like we're not the people to explain this paper to other people.
Again,
on,
you know who is?
Satvik.
Satvik.
Yeah. Next time we'll fly Satvik out here. Oh, we should visit him in Chicago.
Oh, that's a good point. He's in Chicago. Every time we go to Chicago, we text a bunch of people. We never text him.
Yeah.
You say thinking of him as in Santa Barbara.
Yeah. Okay. Well, we're going to Chicago end of April, so Satvik will hit you up. But yeah, thanks for reading it with me.
Myles O'Leary, if you ever listen to this, come get a coffee with us before we get fired. We're not around for much longer, unfortunately. But do we have anything else? Oh, I guess going out. Oh, no. Possible further problems, if necessary. Go in order. What do we think is intellectually beautiful about this paper? It's a active nematic solid. Enough said. It's a pretty cool idea, guys.
I feel like the idea, the title is
yeah. If you could have added one thing to this paper, what would it be?
I think if you're going to talk about Hydra so much, you should show some Hydra data.
Okay, mine is... That's a great... You always have such good answers to that question. Mine is I would have liked an extremely large simulation with... What are the wrapping boundary conditions called again?
Yeah, periodic.
Periodic boundary conditions. Look, we're being recorded live. This is hard, guys. Fridtjof is young. This Princeton guy is young. Where's like a good simulation of this shit? Anyways, I thought that from a simulation perspective, I could have gotten something a little bit bigger that gave me a little bit better intuition of what I could experimentally expect
to see. Yeah. Anyways, I think theory papers can really inspire beautiful experiments.
Soft outro, business announcements, clear-ups from the previous episodes. We've been doing this
weekly update.
It's not what we want it to be.
Yeah, I think
it'll probably die. We might try it one more time.
I think we have to do something more fun and less papers, like fewer papers, because even if you go through your website to look at the papers that came out, 30 papers is still a ton of papers to scroll through.
But on the other hand, we found this paper because of
yeah, but it was in our
features.
In our features.
Yeah.
So I maybe we just go with features.
But my one for next week is oxygen depletion in biomolecular condensates is dominated by macromolecular density.
Okay.
Is not from our features.
Okay.
So I don't know.
Yeah, asterisk.
So it's not what we want it to be. It's taking more time than we want it to take. We don't like making it. You don't like watching it. We have like 9 views on it. So we're trying to figure out a format for that. That would be like a kind of fun weekly update, pseudo news.
Yeah, pseudo creative thing.
If you have ideas, let us know. So shout out to other like experimental scientists. If you want to do something with us, we have like some other ideas that we would like to do, especially with people who are living far away from us who we want to stay in touch with. You probably got an email from us, but nobody responded to the email. So, and then I think that we're going to move these episodes to every Wednesday. That's certainly when the last one came out. I expect that's when this one will come out as well. And try to save the Monday spot for some sort of supplemental news thing. Yeah. And maybe nothing will get put into that slot, and try to save the Friday slot for something silly. So this is probably coming out on Wednesdays from now on. Let us know if you don't like that. If it was like part of your weekly routine to get these on Mondays, that's fine.
Yeah, I think that's everything we need to talk about.
If you are hiring and you could afford to hire 2 scientists, seek us out. Our runway is pretty short at this point. Hopefully we get to keep making these for many years, but I was thinking that we might just like make 20 of these 1 month and then have them queued up so that even when we have to disappear, these updates keep coming out.
Yeah,
or these
just for a little bit.
Out.
I think anyways, it's an interesting idea.
Yeah. Just like in May, we'll know for sure that like we just didn't get to continue doing this, and we could just spend all of May just like doing nothing but journal clubs.
Yeah, which would be an interesting
farewell.
swan song.
A summary for Asya by the picker. So for Asya, broadly in the world, why did you, Linnea, care?
I cared because I was really enamored with active nematics when I was a PhD student. I remember the first time Zvonimir showed me, during my interview, he showed me a video of the microtubule-based active nematics. And I had prepared, to meet with Zvonimir. I had read all of these virus membrane papers. And we sat down and we were talking about the active nematic paper. The dynamics are really captivating, and they captivated me for a long time. And this seemed like a possible paper to hint at that these dynamics could be seen in other materials. And to me, that seemed beautiful. And I'm always looking for new perspectives on old ideas. So that's what I was excited about with this paper. And I think to some extent it delivered. I think it still has a long way to go, and kind of similar to what happened in active matter. Like, you really need an experimental system that unequivocally and beautifully shows these dynamics.
You know what that experimental system is going to be?
Hydra.
Yeah.
Hydra. Hydra. Hydra.